The James Webb Space Telescope, humanity's most sophisticated tool for exploring the distant reaches of the cosmos, has once again defied expectations by revealing stunning new insights into one of the most overlooked celestial bodies in our solar system. Pluto is hiding something that has scientists panicked and questioning everything they thought they knew. Declassified photos from the James Webb Telescope have revealed shocking details under its icy surface. What else could be lurking in the shadows beneath that frozen shell? Let us dive into this discovery that will reshape the quest for alien life forever. Pluto, once dismissed as a frozen and inert dwarf planet residing at the edge of the Kuiper Belt, Pluto has undergone a dramatic transformation in the eyes of scientists and the public alike. Thanks to Webb's unparalleled imaging and infrared capabilities, the telescope has delivered high-resolution images and spectral data that have unveiled an unexpectedly dynamic and complex world, teeming with geological, atmospheric, and potentially even biological activity. This far-flung icy body is no longer just a relic of the solar system's formation, but has emerged as a possible haven for microbial life. One of the most groundbreaking revelations is the possibility of a vast subsurface ocean beneath Pluto's icy exterior, particularly below the heart-shaped region known as Sputnik Planitia. What was previously believed to be merely a frozen nitrogen plain is now thought to conceal a colossal body of liquid water, kept from freezing solid by a thick insulating layer of ice and internal heat generated from radioactive decay within Pluto's rocky core. The existence of such a notion not only expands the list of potentially habitable environments in our solar system, but also challenges conventional thinking about where life might arise. These subsurface reservoirs, hidden beneath layers of frozen crust, could provide stable environments shielded from harsh cosmic radiation and temperature extremes, conditions not unlike those found around Earth's own deep-sea hydrothermal vents, where life thrives without sunlight. The geology of Pluto further reinforces its active and evolving nature. Webb's observations have revealed immense ice mountains that rival the size of Earth's tallest peaks, stretching thousands of meters high alongside smooth plains that hint at relatively recent resurfacing events. These features are unmistakable signs of geological activity, astonishing for a world so distant from the Sun. The mechanism behind this activity is likely a process of slow convection driven by internal heat, causing nitrogen and other ices to slowly circulate beneath the surface. The presence of tectonic ridges and possible cryovolcanoes, ice volcanoes, further indicates that Pluto's interior is not dormant. It pulses with life in a geological sense, reshaping its terrain over time. This puts Pluto in the same category as other geologically active icy bodies such as Europa and Enceladus, both of which are also thought to harbor subsurface oceans and are prime candidates in the search for extraterrestrial life. Pluto's closest companion, Charon, adds further intrigue to this system. Unlike most planetary moons, Charon is so large relative to Pluto that the two objects are considered a binary system orbiting a common center of mass that lies outside of either body. This unique gravitational dance generates tidal forces that may contribute to internal heating on both worlds. Charon's surface features, such as massive canyons and reddish patches, hint at a geologically rich and chemically diverse environment. Some scientists even speculate the material may be exchanged between Pluto and Charon through impacts or outgassing events, enabling a shared chemical evolution that could include ingredients essential for life. The reddish stains on both Pluto and Charon's surfaces are believed to result from the presence of tholins, complex organic molecules formed when ultraviolet radiation breaks down methane. These molecules are not just cosmetic. They represent a significant step in the chemical pathway toward life, similar to prebiotic compounds that existed on early Earth. Webb's infrared instruments have also revealed surprising complexity in Pluto's atmosphere, which, though extremely thin, is composed of layers of nitrogen, methane, and carbon monoxide. This tenuous atmosphere undergoes dramatic seasonal changes as Pluto follows its elongated orbit around the Sun. When Pluto is closer to the Sun, surface ices sublimate into gases, forming a temporary atmosphere. As it retreats into the colder reaches of its orbit, the atmosphere condenses and refreezes onto the surface. This cyclical transformation is unique in the solar system and offers a fascinating laboratory for studying atmospheric physics under extreme conditions. Adding another layer to Pluto's mystery is the potential interaction between its subsurface ocean and surface chemistry. If water from beneath the crust occasionally breaches the surface through cryovolcanism or tectonic cracks, it could interact with the tholins and other surface materials to create more complex organic compounds. This possibility has profound implications for astrobiology, suggesting that Pluto is not only geologically and chemically active, but also biochemically promising. The detection of possible tectonic shifts, underground reservoirs, and localized thermal anomalies by Webb reinforces the idea that Pluto's interior is dynamic. The next logical step, as envisioned by scientists, would be to send orbiters and eventually robotic probes capable of penetrating the icy crust to explore these subsurface regions directly. Such missions are technologically challenging, but increasingly within reach. Concepts being developed include ice-penetrating heat probes and miniaturized submarines designed to explore extraterrestrial oceans. These advanced tools could confirm the presence of microbial life and unravel the mysteries of Pluto's internal structure. Beyond the planet itself, Webb's data has also brought attention to Pluto's interactions with the broader Kuiper Belt environment. Previously considered a passive member of this distant region, Pluto now appears to be actively engaging with its surroundings. Observations show evidence of dust exchanges, micrometeoroid impacts, and transient icy plumes, suggesting that Pluto's surface is shaped not only by its internal heat, but also by the forces of deep space. Intriguingly, Webb has detected subtle variations in charged particles and energy signatures surrounding Pluto, pointing to interactions with the solar wind and Kuiper Belt debris. Although Pluto lacks a strong magnetic field like Earth, these energetic exchanges offer valuable insights into space weather in the outer solar system and hint at previously unrecognized forms of planetary magnetism and protection. These findings collectively paint a picture of Pluto as a vibrant, multifaceted world whose mysteries continue to unfold. They also rekindle the debate over Pluto's status as a planet. Since the International Astronomical Union controversially reclassified Pluto as a dwarf planet in 2006, public and scientific opinion has remained divided. The new evidence of geological activity, complex atmospheric behavior, and potential habitability has strengthened calls for Pluto to be reinstated as a full-fledged planet. Regardless of classification, Pluto now commands a central role in the ongoing narrative of planetary science. The revelations from Webb have also ignited a cultural resurgence around Pluto. Once an underdog in the pantheon of celestial bodies, Pluto is now a focal point for public fascination and academic inquiry alike. Enthusiasm for space exploration has surged, with new collaborations forming between governments, space agencies, universities, and private firms to plan the next wave of missions to this distant world. In classrooms, news outlets, and online forums, Pluto's story is being retold with renewed passion, inspiring a new generation of scientists, engineers, and dreamers to push the boundaries of what we know. As we look ahead, the role of Pluto in shaping our understanding of life in the universe cannot be overstated. Its geology, atmosphere, and potential ocean all suggest that the building blocks of life may be more common and more varied than we previously imagined. This challenges the traditional notion that habitability is confined to planets. Within a narrow range of distances from their star, the so-called Goldilocks zone. Instead, Pluto suggests that internal heat, chemical energy, and protective ice layers may provide all the necessary conditions for life even in the darkest corners of the solar system. These insights compel scientists to reevaluate the habitability potential of other icy bodies such as Neptune's moon Triton, the dwarf planet Ceres, and even rogue planets drifting between stars. If Pluto, once thought to be a cold and lifeless rock, can support the prerequisites for life, then the universe may be teeming with similar worlds awaiting discovery. The James Webb Space Telescope has not only transformed Pluto from a frozen afterthought into a scientific treasure trove, but has also fundamentally altered our understanding of what constitutes a habitable world. As the telescope continues to collect data and future missions are designed to follow in its wake, Pluto stands as a beacon of possibility, proof that even the most remote corners of our solar system can harbor profound secrets. The dream of robotic explorers diving into its subsurface ocean and bringing back samples of alien water, perhaps even microscopic life, is no longer the realm of fiction. It is the emerging reality of 21st-century space science. The ongoing exploration of Pluto will not only illuminate our own origins, but may also help answer the age-old question of whether we are alone in the universe. These stunning revelations about Pluto have reignited debates that stretch beyond scientific curiosity, touching on cultural identity, academic legacy, and humanity's need to classify the cosmos in familiar terms. For decades, Pluto held a special place in the public imagination as the ninth planet in our solar system. Its sudden reclassification to dwarf planet in 2006 by the International Astronomical Union (IU) triggered widespread controversy and emotional responses, particularly among those who had grown up with Pluto as a household name. But now, with the James Webb Space Telescope peeling back the layers of Pluto's mysteries, those old arguments are flaring up again with renewed urgency and data to back them. Many scientists, emboldened by the latest findings, are pushing for a reconsideration of what defines a planet. The traditional view centered on orbital dominance and mass may be too simplistic in light of Pluto's incredible geological complexity, potential subsurface ocean, and atmospheric dynamics. If we judge planetary status by geological activity, chemical processes, and potential habitability, then Pluto could very well deserve reinstatement as a full-fledged planet. Its behavior defies expectations for an object supposedly too small and distant to be active. Rather than a frozen fossil of the solar system's formation, Pluto behaves like a living world, sculpted by internal heat, shaped by external forces, and potentially incubating the building blocks of life beneath its icy crust. The implications of this are far-reaching, challenging not only our classification systems, but our understanding of where life might thrive. Pluto, once dismissed due to its remote location, now forces scientists to reconsider what makes a world biologically promising. Traditionally, the habitable zone or Goldilocks zone was limited to a narrow band around a star where temperatures allowed for liquid water on a planet's surface. But Pluto demonstrates that internal heat, combined with insulating ice, can create habitable conditions far beyond the reach of solar warmth. It introduces a revolutionary idea that life could exist in subterranean oceans sealed beneath kilometers of ice, warmed from within. This concept doesn't just apply to Pluto. It hints at possibilities for life on similar distant objects like Eris, Makemake, and even rogue planets wandering through interstellar space without a parent star. If these bodies possess enough internal heat and water, they too could support life. Such a shift in perspective represents a seismic evolution in astrobiology, one that Webb's revelations have accelerated dramatically. This paradigm shift has also ignited a fresh wave of public interest and wonder. Social media platforms, science forums, and educational institutions have lit up with discussions about Pluto's resurfaced potential. Children are once again drawing Pluto in school science projects, not just as a tiny lonely ice ball, but as a vibrant world with heart-shaped plains, mysterious mountains, and chemical signatures that hint at something more profound. The new narrative inspires not just admiration, but a sense of possibility. If life can persist in such an inhospitable location, what other secrets might the cosmos hold? These questions are pushing a new generation of scientists to pursue careers in astronomy, planetary science, and engineering, determined to be part of the next wave of exploration. Governments and private space agencies are taking notice too. Several collaborative proposals are already underway for follow-up missions to Pluto, some suggesting orbiters equipped with advanced radar to penetrate its icy crust. Others proposing innovative cryobots and hydrobots designed to melt through the ice and swim in the hypothesized subsurface ocean. These missions will require massive technical advancements, particularly in autonomous operation, communication delays, and power generation in deep space. But the payoff could be historic, the first discovery of extraterrestrial life within our own solar system. Even now, the Webb telescope continues to stream back data that deepens our fascination. Recent spectrographic analysis indicates unexpected variations in surface chemistry from region to region, suggesting either diverse geological histories or ongoing dynamic processes that constantly renew and reshape the terrain. Some patches reflect ultraviolet radiation differently, indicating the presence of complex hydrocarbons and possibly even amino acid precursors. This variability supports the idea that Pluto is not just geologically active but chemically rich, perhaps even possessing regions more favorable to life than others. Meanwhile, attention is turning toward Charon, Pluto's largest moon and gravitational partner. Observations show that it too may contain a subsurface ocean, though likely older and less active than Pluto's. Still, the giant canyons and surface fractures on Charon hint at a violent and geologically significant past, perhaps tied to tidal interactions with Pluto itself. These interactions may continue today, subtly shifting the internal heat and chemistry of both bodies. There is even speculation that microbial life, if it exists on Pluto, might somehow be transferred to Charon via impact events or shared atmospheric material, a form of intermoon panspermia that would redefine our concepts of habitability and biological dispersal within planetary systems. Pluto's newfound complexity also raises fundamental questions about solar system evolution. How did a world so small and remote come to possess such a dynamic and potentially life-supporting environment? One hypothesis suggests that Pluto formed in a region rich in radioactive materials, enabling it to retain internal heat far longer than previously thought. Another proposes that collisions or early tidal interactions generated enough heat to kickstart subsurface convection and ocean formation. Either way, Pluto's history may hold clues to the development of other icy bodies across the solar system and beyond. It serves as a laboratory for testing theories about planetary formation, internal differentiation, and the limits of geological activity. Some researchers are even exploring whether Pluto-like objects in exoplanetary systems could be detected and analyzed using the same infrared techniques Webb employed. If we can find similar signs of subsurface oceans and complex chemistry on distant exodwarfs, we might be able to identify a new category of potentially habitable exoworlds that have until now gone unnoticed. The excitement has also spilled over into artistic and cultural spheres. Writers, filmmakers, and artists are embracing the new image of Pluto as a vibrant and mysterious world. Novels and short stories are reimagining Pluto not as a cold dead end, but as the cradle of alien life or a future outpost for human colonization. Documentaries and podcasts are devoting hours to exploring its shifting status and the scientific revolution it represents. What was once an overlooked corner of the solar system is now a wellspring of inspiration. Educational campaigns are adapting too, with new curriculums designed to incorporate Pluto's discoveries into science education from elementary levels to university courses. Interactive simulations, virtual tours based on Webb's data, and augmented reality applications are allowing students to explore Pluto as never before, walking its icy ridges, diving into its hypothetical oceans, and studying its dynamic weather and geology. In this sense, Pluto is becoming more than a scientific subject. It's becoming a portal for public engagement with space science at large. What lies ahead may be even more thrilling. Plans are being drawn up not only for direct exploration of Pluto, but for missions deeper into the Kuiper Belt. Scientists now believe that the region could harbor dozens, if not hundreds, of Pluto-like bodies with subsurface oceans and complex chemistry. Each could offer unique insights into the variety of planetary formation scenarios and perhaps serve as stepping stones for even more distant exploration. If Pluto is the key that unlocks these secrets, it will have more than earned its place among the great explorers of our solar system. The data from Webb has not only transformed how we view one small world, it has opened the door to a broader understanding of life, habitability, and the ever-evolving narrative of our cosmic neighborhood. The story of Pluto is no longer about what it isn't, a planet according to outdated definitions. It's about what it is,